Thank you very much for your introduction. And actually, I'm gonna present a small proceeding from some recent work from 2019, 2020. That was some early beginnings with AI and machine parameter adaptation. And we started at this time with the CNC milling process. So let me first introduce myself a little bit. Here you see a little bit of my portfolio. I'm mostly into mechatronics, developing different kinds of robots, different kinds of demo facilities, automotive assistance systems, and also collaborative robots, IoT systems, and education material. So from this development steps, I continue with my proceeding. The AI-CNC algorithm we developed is an algorithm that is able to find optimized parameter settings for CNC milling process in real time by 10 to 15 frames per second or with a snapshot system. And we have a camera setup and some specified test patterns they created with different machine parameter settings. And according to the test patterns, there is an assessment process by AI, and then there's a correlation process from optimized from best judged AI results to the machine parameter settings. Here you see a little context diagram of the system setup. Also, we have in general a hospice. The hospice, there's an instance of our app running, and the app has a user interface, some data storage algorithm, and of course the neural network structure included. And interconnected to this hospice, there is then our assessment system. In general, it's a simple camera and some illumination system. So we have a kind of equal illumination to each part. So here's a little bit or a little overview at the software architecture in general. And the software, we have the app and the data storage is connected. We store the patterns of the the captured patterns there, and we label them. And after labeling, we are able to train the AI with the data sets. And in special, there's also a human machine interface for the human. So we visualize defects and so on the parts. And the target is to run some unknown materials. The machines have mostly the problems, and there are some unknown material combinations. Then it needs time to find out the best parameter settings, and so we with our system, we are able to shorten the running process of the CNC machine. We have different patterns like circles or squares. We also tried out some line patterns and so on, but circles and squares fits most for what we're doing. Here I must apologize myself. There's a little German inside, but the most important parts are in English. So we have here a little workflow diagram of the on the recording algorithm, and then on the assessment algorithm on the right. On the left is the recording, right is assessment algorithm, and then generally we go, we make the pattern recording, then we ask, is a webcam connected? Then we record the sample part, we give some user feedback, and then after this, there's a cluster algorithm that wait, I highlight my mouse. So here there's a cluster algorithm. So, and then it automatically cuts out the patterns of the samples. And then it creates a folder and saves it there. And then it goes to the assessment of the recordings. And then there's a user assessment from a manual assessment at first to yeah, to put into good or bad folders at first for the training situation, and then after assessment is done, the network is trained, and after that the assessment is done automatically. So yes, also here you see a little overview of the general user tabs of the software. You have a recording tab and then a special tab for yeah, choosing your working folder, and then you have the parameter prediction tab, also that is able to load the images and label them as IO or NIO, and also and then we have the AI training tab for the assessment of the labeled image. Here you see a little bit the appearance of the tabs. Also we have here the recording tab. Also here you can connect any kind of webcam. Also it's kind of USB interface. Webcam is maybe not so the right name, but in general we use some kind of simple webcams we had there, and so we name it like this. And so and then we record the parts, and after recording we cluster them and divide them into single patterns. So and then here you see on the right side the training tab for the AI. Here you have a pattern that is cut out of the sample part, and so you have a cluster pattern, and then you see here's a kind of binarization process, and and then after this, we have the occlusion sensitivity map overlay. Also, so we have here some kind of overlay where we mark special defects at the parts for the user. So yeah, this is the both most important parts of the process. And we have here on the right our milling machine, and on the left our assessment system. You see here around is LED strips, and here you have the webcam included. And we make then the images, the image recordings with this USB webcam. And here we are milling the sample parts, and it's a DMU 65 monoblock 5-axis CNC milling machine. And then for the first test period, we use a polymer, and the polymer will be described a little bit later. So here you see what happens. Also we on this pattern, we have at least 9 patterns, and for each circle or square we are running, we use here a special combination of cutting speed and feed. The dipping feed and cutting rate and cooling methods is and also the tool is the same. And so we make a variation of cutting speed and feed according to some desired borders. And so in the experiment with the polymer, we used 105 to 420 meter per minute at the cutting speed, and feed parameter from 401.1 to 1604.4 millimeter per minute. And so this was the variation we did, and you see, and for each pattern we use then different setting combinations. And after we did this, then you see you have in this sample patterns, you have then the combination feed 1, RPM 1, feed 2, RPM 1, and so on and so on. And we go through the parts, and we judge the surfaces. Or you see with your eyes already that there's some difference in the surfaces. occurring to the different machine parameter settings. And so we have here on the left side a little description of the sample parts we are creating. It's a 140 millimeter thickness part, or thickness 5 millimeters. Polymer part is a polyvinyl chloride PVC material. And the part density is 1.3 to 1.45 gram per cubic centimeters. And then we have thermal conductivity factor, also it's some important for milling. And we have here kind of yield strength of the material. And then for the circular patterns, we use 30 millimeters in diameters. And for the squared patterns, we use edge lengths of 30 millimeters. So our algorithms is doing this. Also it makes a binarization of this circuits, and it finds the centroids of the circuits. So when we find the centroids and make the binarization, according to the binarization, we find the centroids. Then we can cut out these parts very precisely. So we make the 9 sample. We make the sample parts with the 9 patterns, and the 9 patterns will be cut out each. So then we use a neural network. At the first approach, I must say it was the very beginning of my research at this. And so we were at 2019. Yeah, we need a little bit more experience in artificial intelligence. Also it's really crazy what happens within the last 3-4 years in this topic. But at the past, also we use simple SqueezeNet neural network, but we exchanged some layers, and especially the input layer was changed, so we can adapt it to the webcam, and also we make a low resolution, so we can save some time and make the frame rate a little bit higher when it goes to real-time webcam observation. So we use a pretty simple PC, as it's a Core i5 6000K processor. It's a pretty old one, but it's okay, and so it was suitable for our system. So here you see a little bit in detail the network structure. Also here before you see we have at least 20 main layers, and so there's a network is consisting of some fire modules, pooling layer, layers, and so on, and at the end, we have some softmax function that gives the weights for each assessment of the network. So, and here you see you have at this point you have this ReLU. Also ReLU is a rectified linear unit. I think this is the short term for this. This activation function, and then we have the softmax layer at the end that gives us the probability function of the probability of each result. So wait a moment. So here's the learning proceedings of this. As we have then some kinds of sample patterns. At this we use 75 epochs for learnings and 150 iterations, and you see it's a pretty old experiment, as it is really some of my old experiments. And we use a single CPU training method. And here you see the learning rate of the network, and you see even with this old hardware setup, we need at least 4 minutes 22 seconds for learning. And I think it was kind of just only 20 patterns we had for training. And here you see a little bit of the parameter settings. We had a drop factor of 0.7 every 10 epochs, and so on, and we have the epsilon of 1e minus 7. And you see, also here's the accuracy, the training accuracy, and here's the loss rate. We didn't have so many sample patterns at this time, and so yes, also it's not so well trained the network, but it's okay for us. Also here in the left you see the original pattern, and on the right you see then after the assessment the occlusion sensitivity map overlay from this network. And so you see some kind of intensity also for the defects occurring, but the network here is a very fast trained network. Also, so it was like we need more training patterns at this time, and so the accuracy would also be higher and for marking the defective parts. At least here's some of our results. As we used at the initial training, we used only 20 images, of very, very poor and low image opportunities we had at this time. And but even with this small amount of images, we got about of 6. Also I would say there was 60% correct judge. Then we have 20% false assessment and 20% with no correlation of the results. And what happens now is like we have then here the good assessment, neural network or expert or both or whatever. And and then on the left side we have the pattern number and the cluster pattern number that is given out. And then we have the amount of activation for defects here, and then we go and give a kind of we find the parameter settings with the best results, and then we make a kind of this is not ready, but it's in planning. We make a kind of optimization so that we find the maximum amount of cutting speed and feed of the machine. And of course, we need to produce many parts and save time and make optimized parameter settings. And so we go to the very edge and find then, according to our assessment, the optimized machine parameter settings. Okay, in general, this was my small presentation. Yes, here's a small conclusion. Also we developed an initial prototype, and we tested it in laboratory conditions with this polymer part, and according to the DMU 65 CNC-Milling machine. And so we only have a small number of training data left. And so the initial results give us a good opportunity to continue this. And in the future steps, we have to target to create a more robust network structure. We have to test it under industrial conditions, and maybe we use a VGG19 network, or we make our own network. And the results have of the neural network has to be evaluated in detail. We didn't do this at that time. And currently we are more into die casting and welding. And so the CNC milling, we had not so many time to continue the research. So I presented here, and maybe after we get our results from welding and die casting, then we adapt this also to the milling machine process. So thank you very much. Thank you for kind attention, and please feel free to ask some questions, or even contact me if you want.